So now I'm going to talk a little bit about using Robotics Toolbox for the analysis and plotting of various animations and configurations of the arm. So in section 4.2, you're asked to calculate forward kinematics. So I already went through how you can actually use Robotics Toolbox using the link command and the serial link command in order to build up link homogeneous transformations. And this is a really good way of checking that your Denevit-Hartenberg coordinate system is correct, and it actually gives you the same results as you got when you did the analysis by hand. So I'd very much suggest you do check every single link homogeneous transformation and make sure it agrees completely with what you had before. I also strongly suggest you not to evaluate it at any particular value of theta, which is the control variable. Leave theta as a symbolic variable, and then you've got the proper equation for each of these parts. You can then, well, obviously you've used link and you've used serial link to do a single link robotic arm, which is basically about as simple as you can get. And you can use the member functions to get the kinematic transformation from the endpoint back to the origin. However, you can use serial link to link lots of links together. So you can link all the links together in your robot and get the overall forward kinematics as well. And you need to calculate that and show what it looks like in the results. So one of the nice things about building things up using the robotic toolbox is because it's got a lot of functionality built into it to let you visualize and all this kind of stuff. So you can actually build your serial link robot, and then you can use the plot member function to show you the default configuration. And you have to give it what the default, what the values of theta are in the default. The only thing to watch out for is that there is actually a bug in the latest version of how it works with the latest version of MATLAB, and basically you need to set what I've done. The important thing is to set the view to 3D, right? So this is what I always do in front of when I'm doing the plot now. First of all, I set the workspace up, so you say the number of units you're actually going to show in 3 dimensions. You then call view 3, which basically tells the view it's 3-dimensional. And then you can put hold on, grid on, axis, set the axis size, and then you can do your plot. And when you're doing the plot, you give it basically, what do you want the angles of the robot to be when it's plotted, and that's where you give it this array or this matrix, which gives it the default values. And these other options are also sometimes useful. If you don't do this view 3 thing, it generates horrible errors and it's very confusing, but I did manage to find on Google somebody who found the solution to it. So another thing to bear in mind in your SainSmart design is I'm not going to tell you which one, but there is one particular joint where there is the default configuration also has a default offset on one of the Z axes, right? So one of the control thetas has got an offset on it in order to get, if you like, the configuration of the SainSmart arm that I gave you in terms of the coordinate frame. So you have to bear that in mind as well when you're setting up default configurations. One of the nice things about Robotic Toolbox again is it does have this really nice interactive mode. So you can use the teach member function and basically it will plot it'll draw your arm out, but it'll give you controllers so you can actually slide values of the control variables over their valid ranges. And in order to do that, you do have to put in some ranges, and just think of something sensible. What kind of range could you possibly have for an angle? It's not going to be more than 360 degrees in all, is it? It's not going to go round and round. So just plus or minus 90 degrees or something like that would be reasonable. Again, think about what happens when you've got an offset in the representation of theta, because you need to deal with that as well. Okay, so in order to give a very naive and basic understanding of what the end effector space is like, I asked you, in fact, to build a scatter plot of the endpoint locations. And this is basically using randomly sampled input angles, right, over the valid range, which then basically are fed into the forward kinematics command, so the FKINE member function, which will then calculate the endpoint for you. And then you can plot these points. You can use a 3D plot in MATLAB to plot this onto your configuration. In fact, I did it in the teach format, so you can actually move around and show the cloud and see how the points can be reached by the endpoint. You did do a practical which was a little bit similar to this in 2 dimensions. I was asking you to use a rand function in order to randomly set θ1 and θ2 on a simple 2-joint planar arm. And the ranges were quite simple on that, so you could probably do that without thinking too much about it. I did give you a function in the lectures, however, if you look back, to let you draw from a uniform distribution between a minimum and a maximum value to give you a certain number of samples. And basically, in a nutshell, all it's doing is using the rand function. And what the rand function does is it samples from a uniform distribution between 0 and 1. And what you have to do, if you want that to appear to be sampling from a different distribution, which is still uniform, you have to add an offset on and you have to scale the value. But that's all explained where I talk about this function, draw from uniform distribution, in the lecture notes. So if you don't know how to do that, have a look at the lecture notes. It is in there for you to use. The final bit really is I'd say the most interesting bit, in as much as this is something which is what you really want robots to do, and that is to get the endpoint to follow a trajectory that you want it to follow. Now, it could be that you've built a robot and you want it to start off by moving and picking something up and then putting it somewhere else. What that involves is, first of all, saying, yeah, I know where I am to start with and I know where I want to go. How am I going to get there? I need to go along a certain path. So one way of getting this robot simulation to do that is to say, I'm going to actually plot my path, or I'm going to calculate my trajectory path in advance. And then I'm going to use inverse kinematics, and there's an inverse kinematic function as a member function of the robot system that you can use, which will then, given the endpoint, will tell you what the control variables are. So given the endpoint that you want it to be at, it will tell you what the angles of the robot arm are. And if you give it basically a lot of points, one after another, it'll tell you all the corresponding angles. And then what you can do is you can then just go through all of those and actually get the robot arm to follow it. So I suggest you build a nice target endpoint location. In fact, I've asked you to do corresponding to moving around the square, and get basically the robot to actually animatedly move around the square. And please do a video of that, right? Do a video, generate an animation, do a video. Please put your student ID in the top part of that particular video, because this is really, if you like, this is everything coming together. If you can do that and you show me that you've done that, I'll believe you've done everything else as well. So that's basically just to confirm it was really you. It just makes it more convincing from my perspective that you really did do the work. So record a video, put a link in the report. You can either put it on OneDrive, but just make sure that when I click the link on the PDF, the video plays. I don't want to grub around looking for stuff on the internet and what have you. Make sure it's a standard format file. And the other thing you can do is you can also put it on YouTube, although the external examiner didn't like the idea of that. He said it's not really good to put things in the public domain, but don't panic. If you don't want to do that, then just do it on OneDrive. Final bit was to actually get you to plot the corresponding trajectories and when you're moving the arm round. And that's just a simple example of using the plot command with multiple traces in MATLAB. Right.